Right. Happy Thursday. Here we are. End of chapter 9. So excited. So, today we're going to do chapter section 9.2. We're also going to do lab 5. I'll go through lab 5. Lab 5 will be super quick. It's a pretty quick lab. Um, we're going to be talking about population means. So the stuff that we're doing tonight corresponds with the stuff from 8.1, section 8.1. So some of that is going to carry over. So we're going to talk about obtaining our point estimate for population mean. We're going to look at a new distribution. We're going to look at t values. Um, it's kind of like a z-score, but it is very specific for our purposes. And I'll show you how to use those. I'll show you the table, and then I'll show you how to do it stuff with the calculator. We're going to do confidence intervals for mean, and then we're going to calculate the sample size needed if we want to estimate the population mean with a special margin of error. So it's the same stuff we did with proportions, but it's just with means instead. So that's today. That's what we're doing tonight, and I'm really excited to get started. I enjoy this. I like the tea table. You guys might not, but I'm weird. I like weird things. There you go. You got to be weird to major in math. Okay. So a point estimate is just the with when we were back up, when we were dealing with proportions, the point estimate was the proportion of our sample that had a specific characteristic. So it was just our p hat. It was the number of people that had a certain characteristics or individuals that had a characteristic divided by our sample size. So the sample mean, the point estimate is just the sample mean. So when you take your sample and you find a mean, it is our estimate of the population mean. So it's all it is a sample mean. That's what a point estimate is in this case. So we're going to find our point estimate here. So remember the pennies from before? We're bringing them back. So we took a sample of 17 randomly selected pennies minted after 1982. And here are the weights. Here are the weights of the pennies. Therefore, our point estimate is just the average weight of all of those, which was 2.464. That's it. Generally, we will round our statistics to one more decimal point than our raw data. So if my raw data has 2 decimals, we'll round to 3. But you don't have to worry about all that because my open math tells you what to round to. So you don't have to worry about all that. Okay. This is really this looks really ugly, but it is not. So we use a t-distribution when we are using a sample. Um, a z-score works really great with larger samples or when we have some information about the whole population. But generally, what we do with the t-distribution is when we have a sample, we will calculate it. And also, t-distributions are used most of the time when we have smaller sample sizes. So if we have a sample size less than 30, we'll use a t-distribution instead. I'm going to explain what a t-distribution is here pretty soon. So um, we are also going to use the t-distribution with n-1 degrees of freedom. Once again, I'll explain that in a minute. So when we have the sample standard deviation, and a sample mean, but we don't know the population mean, or we just have an estimate for it, then we will use our t values. So this right here is how we'd calculate our t value. It is the sample mean minus the population mean if we have it, divided by the new standard deviation. This is the same formula we're using before, except for the S used to be sigma. They also call this the standard error. This is not the same thing as the margin of error. It's just the standard error is what we call this new standard deviation. Don't worry, we're gonna get there. You'll be fine once we do some examples. The examples are where it's at anyway. I give you all of this information and it makes sense after the example. We'll get you there.
Is the whole S divided by the square root of n the standard error? Or
Yes. Yes.
thank you.
Uh-huh. It used to be so in chapter 8 we did sigma divided by the square root of n, but because we don't know the population standard deviation, the S is the sample. So remember, samples get boring letters, whereas the populations get the pretty things, the symbols like the mu and the sigma and all that stuff. Samples get ugly things or boring things. All right. So we're gonna take a look at the z-scores and the t-scores, and we're gonna compare them. So if I take a simple random sample of 1,000, or I took 1,000 simple random samples of size 5, and then I found the mean of each of them, and then I found the means and the standard deviations. I'm going to show you the difference with the z-score and the t-score. Here's the histogram for z. It looks mostly normal. Here's the histogram for T. So, a couple of different things. The Z, it's all like it's bunched up really well, like it's all bunched up right here, and the tails are pretty short. Look at the T value. The tails on these go way out here. So the T distribution looks a little bit different. And I'm not going to ask you to replicate this. I'm not going to ask you to look at both of them, say, oh, yeah, that one's T and that one's Z. This is just kind of giving you an idea of the difference between them. And you're not going to have to choose. Okay. So if I was a statistician in the wild, I would make my decision on whether I use Z or T based on a few different factors, and one of those is sample size. However, in this class, if you are dealing with proportions, you're going to use Z. If you're dealing with the mean, you're going to use T. We're just sticking with that. So don't worry about trying to figure out, does this fit a T distribution? Don't worry. We're going to use Z for proportions um, and T for mean. That's it. I'm not gonna make you like dig deeper and figure out all the nuances. So no worries there. Okay. Here's here's the little bit of a difference there. Z is symmetric, is symmetric and bell-shaped with the center of distribution at 0, and almost everything is in between -3 and 3. Standard deviations. So it follows a normal distribution. It's a nice, pretty bell shape. The T, it's also symmetric and bell shape, but it has longer tails. Woo! It also has longer tails. It's more dispersed. It doesn't, it doesn't follow the standard normal distribution because the tails are longer. Um, so because we are using our sample standard deviation instead of sigma, there is going to be more variability there. So it's not a perfect normal curve. Now it's pretty close and it mostly follows a normal distribution, but it's not exact because we don't have the population information. So it's going to be more spread out. That's perfectly fine. Using the t-values, even if we have small sample size, it allows us to use our analysis tools, which is kind of the point of using t. So that if we have a little bit of smaller sample size, we still can get some accurate information. Okay. T distribution is different for different degrees of freedom. Think sample size. For degrees of freedom, think sample size. Now, there's a little more to it than that, but in this class, that's all you got to think about, sample size for degrees of freedom. It is centered about the mean, or about 0, and it is symmetric about 0. The area under the curve is still 1. Half of it is to the left of 0 and half of it's to the right of 0. And it will, just like the Z, like a regular normal curve, as it goes bigger and smaller in both directions, it will approach, but it'll never equal 0. So these are very similar to Z-score, but it's just more spread out. We just have more in the tails. I'm not going to ask you to replicate this. I'm not going to ask you to give me this information back. I'm just kind of giving you an idea of what we've got here. The most important thing is that our t values depend largely on the sample size. So we will take whatever the area in our tails are, just like we did with z-scores, but we also have to take into consideration sample size, which is degrees of freedom. There you go. Okay. So as I said, the area in the tails of the t-distribution is a little bit greater than a standard normal distribution, once again, because we're using S instead of sigma. And it's going to get closer and closer to the standard normal curve as our sample size gets bigger. So if we have a really large sample size, it is going to be almost exactly the z-score. So that's why I said t-scores are usually used with the smaller sample sizes. So as we get really large sample sizes, it's going to be more normal. It's going to look more like the z curve that we saw. And it's all right. We can continue to use it even with the large sample sizes. It's not a big deal because it does start looking like the curve for the z-scores. So it works. Okay. So take a look here. So the orange one is a t-score with a sample size of 5. Pay attention to what's happening out here. Notice how it's taking longer for it to taper down with a 5. I don't care that it's not as high as the others, but the blue right here is the normal curve. So it's kind of below the normal curve and it's more spread out in the tails. Okay, so my pink one is with 15. So it is not quite as spread out in the tails. Take a look, it's getting closer to the blue and it's getting closer to the blue up here. So I bet you can imagine if my sample size got over 30, it's probably going to match the blue pretty much perfectly. That's why we use the central limit theorem with the sample size is 30. That we can say that it's a large enough sample size for it to be normally distributed because 30, it pretty much matches the normal curve. All right, questions so far? Are we doing okay? Something weird happened to my other computer. Just a second. All right, we're good to go. Okay, so our notation for the t value, we're going to use t instead of z, and we're going to be looking just like we did before at t sub a divided by 2. This is just one. We're just looking at one side on this particular one. So our area in the tails are alpha. This is exactly how we were doing it before. We're just using t values. All right. So I'm going to show you how to do this on your t table. So what I'm looking for, we're looking for the area to the right is 0.2, assuming 10 degrees of freedom. So I am looking for T sub 20 with 10 degrees of freedom. So let me show you what that looks like. I have a T table somewhere. Here it is. Okay, that's not it. Second page of your Z table. So if you printed out the Z table and it has two sides and you were wondering what the heck this little thing is here, this is your T table. Now, the T table is different because it looks at the area in the right. Unlike the Z that goes to the left, the T table goes to the right. So my degrees of freedom are down here. So we want to find the T value that corresponds with 20% in the tail on the right with 10 degrees of freedom. So here's my degrees of freedom, my 10 degrees of freedom right there. And I'm going to go over and right here, it's 0.879. I can see that my T value is 0.879. So 10 degrees of freedom. Now here's the 0.2, 0.879. Let's write this. All right. I go back to my other screen. And I'm guessing it says it on the other page. Look at that. All right, so this shows on this one, their T-table's kind of cool because it has one tail and two tails and all of that, but we're going to be fine. So it has 10 and we're at 0.20 and so 0.879. Okay. So when we're using our T-table, we're going to be using n minus 1 degrees of freedom. So if I said the sample size was 10, we would look at 9 on the T-table. Remember when we were calculating the sample standard deviation and we divided by n minus 1? It's the same idea here, that because we're using sample, we have to go down 1 to account for that variability. So we're going to be using our n minus 1 degrees of freedom instead of n. Okay. Once again, we're going to find the t-value such that the area under the distribution to the right of the t-value is 0.05 with 15 degrees of freedom. Let's go back to our table. 0.05 is way over here. So go down to 15. 15 is here. 0.05 right there. There's my t-table there.
So we wouldn't look at 14?
Well, we will when we're doing our confidence intervals, but this question
Oh, okay.
just wanted us to find it. But yes, you're absolutely right. We would. But they just wanted us to find it, the number. So it's 1.753. Yes, we will when we're doing finding our t-value. Whoa.
Okay, thank you.
All right. Okay, now let's try to get to the nitty-gritty. So, confidence intervals. It's done exactly the same as we were doing with our it's just like when we were doing the ones with the proportion. I would take my sample, my X bar right here, my sample mean. This right here is my t-value. So this is the same thing as when I was saying, I don't like the color of that. Let's see if I can make it stand out more. Okay, let's see here. Whoop, that didn't work. Okay. Change this. Okay. Yeah, I really can't see that. Black. The black is, I just need to not write on top of things. Okay, we're just going to delete it. Okay, this right here. Yep. This right here is the t-value. And that's with n minus 1 degrees of freedom. And we're going to cut it in half because it's two tails. Once again, if my I have a 95% confidence interval, we're going to cut that 5 in half and use 0.25. This right here is the standard deviation. The whole thing together is my margin of error. The whole thing is the margin of error. So I'm going to take my sample mean and I'm going to add the margin of error and I'm going to subtract the margin of error. We call this a critical value. Well, that's what that says right there. And we use n minus 1 degrees of freedom. So once again, we do want our sample size to be less than 5% of the population, but otherwise I don't care. And the funny thing is that in AP Stats at the high school, we don't really care as much about the 5% of the population with dealing with mean. And I don't know why, but I'm just going to leave it be. Doesn't matter. What I care mostly about is that your sample size, if your sample size is small, we're using the t-values, which we're doing here. All right. Let's math this out. I'm going to construct a 99% confidence interval about the population mean. So I know that from this sample, the sample standard deviation is 0.02, and my sample mean is 2.464. Our confidence interval is 99%. So I'm going to use 1 minus 0.99, which is 0.01, and we're going to divide that by 2. So what I'm looking for, 0.005. When I get my t-value, this is what I'm using because that is 0.01 divided by 2. So this is what we're going to use. And my t-value, so my sample, 2, 4, 6, 8, 10, 12, 14, 16, 17. So I'm going to use 16. So I'm going to look for the t-value, and I'm going to use 16df, and we're going to use, hold on, and I'm going to use 0.005, but I'm going to use 16 degrees of freedom. So let's go back to that.
So we're no longer using the level of confidence when you see the 99%.
I am. I took taking the area and the tails. So instead of using inverse norm with 0.995, I'm going to use the t-value because the area in my tails 0.005. But this,
Where did you get the 16 from?
that's because my sample size is 17.
Oh, -1.
Yeah, and -1 degrees of freedom, right? So let me show you. I'm going to go back to my table here. So we're going to use 16 because our sample size is 17. And we're looking for 0.005 because this is the area in the tail. So my t-value is right there. This right there, 2.921.
When do you know when to subtract one when looking at the table?
Every single time you're finding a critical value, you're going to subtract 1 from your sample size.
And will it say like it's a critical value, or is it just like anything that isn't regular?
When we're calculating the margin of error, we just subtract 1.
Okay, thank you.
Okay, let me go back to my other screen. I have all sorts of stuff that I need to erase. Let me get rid of this stuff right here. Okay. Okay, so now I have my t-value right here. I have my mean is 2.464. I need my, I'm going to put it down at the bottom. Make some room here. I need my standard deviation sub X bar. So this is my new standard deviation. So it's going to be the S divided by the square root of n. So it's 0.02 divided by square root of 17. The only time we are subtracting 1 from our sample size is when we're looking for the t-value. That's the only time. Okay. All right. I have Please let me know if my math is wrong. I think it's correct, but let me know if my math is wrong. Okay. I'm gonna put a line here so I don't mess up with my. Okay. I'm gonna calculate the margin of error. I'm gonna do that in this space up here because I'm kind of running out of room. I'm gonna move it up there. My margin of error is t sub alpha divided by 2 times the standard deviation. So I'm going to take the t-value and multiply it by the new standard deviation that we just calculated. So my margin of error here, 0.014, I'm going to go with 2. So this is the margin of error. Just as we did with our proportions, we're going to use X bar plus the margin of error, and I'm going to do X bar minus the margin of error. This is going to get the boundaries of my confidence intervals. So it'll look like this. My X bar is 2.464 plus 0.0142. 2.464 plus 0.0142 equals 2.4782. Now I'm going to do 2.464 minus 0.0142. I got distracted. Sorry. That was my pause. Equals 2.4498. Right. This is my upper bound. This is my lower bound. I'm going to go up at the top to write the way that the answer is going to look. So you'll either see it like this, or like this. One or the other. So the way that I would answer this question is I would say we are 99% confident that the actual mean weight of pennies minted after 1982 is between 2.4498 and 2.4782. That's how I would answer that. Questions?
I think the T part, I know I know it's gonna make sense here soon. I get finding the T and then finding the 16, but what is that number? What is that 2.91 or 2.921? What is that? Is that just called the T value when you find that?
Yeah, it's just a T value. It is our critical value. So it's a critical value. Let me see if I can make some room here. I'm just gonna go back a page because I need more room to write. I don't even have room here. Let's draw a picture. Okay, I'm just going back here. This page doesn't mean anything. I'm just gonna draw a picture. It is exactly what we were doing with the z-score. So here's my mean right here, whatever that was, 2 point whatever. Then I'm gonna go this many standard deviations above. What is it? 2.921. This is plus 2.921 times S. So I moved 2.921 standard deviations to the right, and I moved 2.921 standard deviations to the left. So it's used exactly like a z-score. It's just calculated based on the sample size.
Okay,
Okay.
that makes more sense.
Okay, good. I'm glad you asked that. All right. We're gonna do here's the one that's all typed up. So I like mine better. But here's the one that's all typed up.
Can you go back to the previous one real quick?
Yes.
Thank you.
I know mine's prettier. It's colorful.
Yes, exactly.
Let me know when you're ready.
I am good. Thank you.
Okay, cool beans. Okay. We're gonna move on then. This was the this is just the typed one. Okay. So the website fueleconomy.gov allows drivers to report the miles per gallon of their vehicle. The data below shows the reported miles per gallon of a Ford Focus automobiles with 16 different owners. We're going to treat it as a simple random sample of all of our Ford Focus automobiles, and we're going to construct a confidence interval. I'm going to use my calculator on the computer to put these into my L1, and we're going to use one of our stats together, but I'm going to want to use this data again. That's why I'm going to put it in there where you guys can see it. I'm going to go to my calculator, and we're just going to type in the data in our L1. So hit stat, edit, and I'm going to erase some stuff because I can. And I'm just going to put these numbers in. You can go ahead and do this with me. You'll probably want them also. And there's decimals. I'm really slow. 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Where am I? Did something weird. Darn it. Thankfully, it stays in there. What did I do? Okay, let's go all the way down here. 39.6. Where am I? 32.2. 32.2. Okay, it likes me again. 49, 37, and 36. Give you all a second to catch up. Even though I moved really slow, you probably all have it quicker than me. It's so much faster to actually type on the calculator instead of the computer. So much faster. Does anyone need another moment? Okay, I see you. Yeah. The one benefit of keeping your camera on is you can gesture. Okay, good. All right. So we're just going to do one var stats. You guys have done this 100 times. So stat, calc, one var stats. I don't want anything in L2. I don't want anything here. We only need L1. Go down to calculate. And I'm just going to write down what these numbers are. Uh-oh. Uh-oh. Okay. I'm going to write down my X bar is 36.8. And because this is a sample, we're going to use SX. You're going to use the sample standard deviation. So it's 2.917. All right. Those are the values that we're going to use. That's not where I'm going. So I have my X bar is 36.8. My sample standard deviation is 2.917. I need my T value. I need to look. I'm using a 95% confidence interval. Therefore, 1 minus 0.95 equals 0.05. 0.05 divided by 2. We're going to look for 0.0. I'm out of room. Make things smaller. Okay, 0.0. I need my pen. So we're going to look for 0.025 in our on our T table. Move this thing over to the other side. Move it down to the bottom. I don't know. I hate this thing. Don't know why. It just won't go away. One of these days, it's going to annoy me enough to make me Google it, but not quite yet. Okay, so we're going to use, we have 16 car owners. So we're going to use 0.025, but we're going to use 15 degrees of freedom because we have 16 as our sample size. So go back to the table. 15 degrees of freedom right here, 0.025. So right there. 2.131 is my critical value. Look at, make sure. Yeah, 2.131 is our critical value. Now I'm going to calculate the new standard deviation. So my S sub X bar, it's going to be the standard deviation that we just calculated divided by the square root of 16. Let's all do that in our calculators. I know there's a lot of little baby steps here. That's way too many numbers, but it is what it is.
So you square root from the sample size, and you don't minus it from that?
Right. You just
Okay.
square root.
Just
Yeah. Okay. So now, once again, I am going to take my margin of error is the t-value times the standard deviation. That's how we get our margin of error. So I'm going to move down because I'm running out of room just to find my margin of error. I'm going to use any space I have. My t-value, 2.131 times 0.729. I'm just going to go that far. And that'll be our margin of error. My margin of error is approximately, I'm just going to do 1.55. That's a good number. So let's get our lower bound and our upper bound. Ah, that's too close to each other. My lower bound is going to be my mean minus the margin of error. Is 35.25. Okay. Upper bound. Going to be the mean plus the margin of error. $38.35. Two ways we can answer this. Or I'll give you all a moment before I give you the sentence, let you all catch up. I mean, I know some of you started the 9.1 homework, and I'm sure you saw how my open math bounced all over the place on how they wanted you to enter, like between the doing with the parentheses. Make sure if you're doing it with the parentheses, you're putting the lower value first and the higher value second, and that you're using regular parentheses and not brackets because it will get mad at you. It won't like it. And then your plus or minus. So what I could say is that we are 95% confident that the actual average miles for a Ford miles per gallon for a Ford Focus is in between 35.25 and 38.35 miles per gallon. So what we are estimating is the actual average miles per gallon. So we're estimating the population average. So we have a sample average and we're estimating the population average. I know it's going to be, there's a 95% chance it's in between those two values. That's what's going on here. Questions so far? I'm going to give you a calculator function in just a moment. Actually, I'm going to give you two because I'm fancy like that. Okay. This is still the same Ford Focus thing. This right here is your money. This is the money right here. The calculator function is called t-interval. Or if you want to call it tinterval, you're more than welcome to call it tinterval, but it's t-interval. That's what it is called. There's two different ways we can use t-interval. I'm going to show you that here in a second. Pop over here to my calculator. We already have our data in the L1, which is exactly where I want it. So get out of the screen. We're going to go once again to STAT, go over to tests, and t-interval is right here. It is number 8. So that's what we want. So there's two different ways that you can enter it. Since we have data, we would put it in the data slot. But if you had just the statistics, if it just gave you the mean and the standard deviation, then you would go into the stats slot. But we have data, so I'm going to go over here. and our data is in L1. Frequency, just leave it as 1. We don't have any frequencies, just leave it there. Our confidence level is 95%. This is where you put it. It's 0.95. So this is what we want it to look like. And then I'm going to hit enter and see what it gives me. It gives me, is this the same numbers that we had? Well, there you go. They're the same numbers that we had. I rounded to 2.25 and 3.5, but those are the same numbers that we have. And it gives me my mean, and it gives me the standard deviation, but it doesn't give me the new standard deviation. It gives me the old standard deviation, even though it uses it in the calculations. So I'm going to go back to, hold on here. I don't have another. I'm going to go back to the pennies because with the pennies, it gave us the mean and the standard deviation. So I'm going to go back to the pennies and I'm going to use the other format for the pennies. So once again, I'm going to go to stat calc, go down, oh no, stat tests, go down to T interval, enter. And I'm going to go to stats because I have information I can enter. So my mean for my pennies was 2.464. My standard deviation for my pennies was 0.02. You're not calculating the new one. Just put in the one that they gave you. My sample size for the pennies was 17. And my confidence level is 99%. Then I'm going to go down to calculate. And let me see here. Did it give me the same numbers? It did give me the same numbers, 2.4498 and 2.4782. I love when that happens, and it'll just give it to you. Questions so far before I give you the next calculator function?
Could you show where you were writing notes? I was trying to ask a question earlier, but my mouse wouldn't work.
You know, that totally happens.
That screen.
This one?
Yes.
Okay.
So on the left in purple where S means sample standard deviation.
Yeah, this right here. Yes.
Yes. And then what does the S sub X bar mean?
That's the new standard deviation or the standard error.
Oh, okay.
Standard error. There we go. Or new standard deviation. Because this is a sampling distribution, we need to use that for our margin of error calculation. And just think, 8 weeks ago, none of those words meant anything to you. And you guys have a whole new vocabulary now. I say all these words that are just new to you, and you guys are using them like it's nothing. It's awesome. Okay, can I move on? Are we good?
Yes, thanks.
Okay. All right. So some people don't like the tea table. Or, for example, I'm on the tea table right here. If they gave me, let me go down here. Notice how on my tea table, once I hit 40, it just jumps 10 at a time. It's not exact. And technically, if they gave me a problem that was 45, I could take these two numbers and I could average them. Like, let's say I was doing zero point 0.2 for 45, I could take 0.851 and 0.849, and I could just average them and use 0.850. I could use that. Not a big deal. But it becomes even more difficult when I jump from 100 to 1,000. And this is why we generally go to Z scores once we get there. And that's what this is saying right here. Hey, if you're going to go more than 1,000, just use a Z score. But sometimes things are weird. Sometimes they give us strange. They want an 85% confidence interval or 83% or something weird that's not in our table. So we have a fancy calculator function. Now I'm going to tell you, I don't think the TI-83 has this. So I'm hope you just do the best you can with your table, but I could tell you I'm going to be really nice to you on the test and use ones you can find in the table. If you get a weird number or you just don't want to use your table, if you do second vars, you know how we have inverse norm? We also have inverse t. So inverse t, you put the area in the tail and the degrees of freedom you want to search, and it'll give you that t value. So I'm going to use what we just did with the miles per gallon, go into inverse t. The area in the tail that I was looking at was 0.025. My degrees of freedom, because I had 16, I was doing 15 degrees of freedom. That's a 14. 15 degrees of freedom. That's a 5. What the heck is wrong with me? There we go. 15 degrees of freedom. And then I just hit enter and then enter again. And it's going to give me, now it gives me a negative. Just know you need the positive. Just know that this t value is always going to be positive. But it gives me the same number that I just found.
Can you go back to the inverse t so I can see what I was writing it down? I'm sorry, as you were talking.
No problem.
Inverse t.
Right there. That screen right there.
Degrees of freedom. Okay, so your area is already the t value that you've minused
I've
one
already,
from, and then you're gonna copy that down to the degrees of freedom, the 15 still.
that's right. I subtracted it from 1 and divided by 2.
Yeah.
And
Okay.
then the degrees of freedom is subtracting 1 from your sample size. And then hit enter. And then it'll give you a negative, but that's okay. Just make it positive because we don't use negatives for our t value here. Just use positive.
Okay, thank you.
You're welcome. So inverse t is beautiful if you don't want to use your table, even though I kind of like the t table. T table is just kind of cool, but I'm also weird, so don't listen to me. But
You are, sorry, you are right that it is not on the 83.
yeah, so you're
But
gonna just
I
have
mean, the T table is not hard to follow though. It was really easy to find it.
so if you want if you send me an email for an online calculator emulator that you just in case, I can send you instructions on how to get to a free one. If
Okay.
you want to a TI-84, you obviously can't use it during a test, but the test is going to have good numbers.
Yeah.
So, but if you decide you want that emulator, just let me know. Anybody can do that, and I'll send it to you.
Do you want us to send you an email from our email or just a message in the class?
Either way,
Like,
either
okay.
way is fine. Because
Okay.
the thing is it's kind of cheating because there's a college website where there's a placement test on the college website.
Uh-huh.
And they provide a TI-84 emulator that looks just like mine. And
Okay.
you don't actually have to take the test to get to the emulator. You just have to pretend you're gonna take the test.
Oh, okay.
The emulator will pop up. So,
Gotcha.
and I found it and I was really proud of myself. So I can share it with you. So if you want,
That's very cool.
yeah. So if you want that, just send me a message and I'll get that to you.
Okay, I will do that.
All righty. Okay.
Thank you.
You're welcome. Okay, let's go back. All right. So now we're going to jump to finding sample sizes. Are we okay with finding confidence intervals? Are we feeling kind of okay? I know once you do the homework is when you rubber meets the road, but okay. All right. Sample sizes. So our problem with the sample sizes, it's a little bit different than here, because remember what our issue that we had, back up here. Remember when we were dealing with the proportions, our issue was that we didn't have a p hat. That was our issue with the proportions. We kind of have a similar issue here. When we're doing them with the means, we use t-scores or t-values, but we can't use a t-value if we don't know the sample size. Therefore, if you are finding the sample size of a sampling distribution of mean, or in order to do this confidence interval, for that sample size, we have to use the z-score. Because we don't have a sample size to use the t-score, we have to use the z-score. So what we do is we take the critical value we find in the z-score, and it's still alpha divided by 2, the same way we did it on Tuesday. Multiply it by the standard deviation, which is our sample standard deviation, not the new standard deviation, the sample standard deviation that we are given in the problem. So don't calculate the standard error or the new standard deviation. This is just what we got with our problem. Divide it by the margin of error, then what you get, you square it. So we're going
So
to do,
this is only determining the sample size required for a mean.
yes. I do have at the very end, I have 2 slides that compares the 2 things. So I will have I know some of you really like the breakdown and all of that, everything consolidated. At the end, I have 2 slides that consolidates all of it. Okay, I'm going to give you a second. Okay, moving on. Are we good? The capital E is just margin of error. Instead of ME like I do, they think they're cool and they just drop the M. They're not cool. They're not. They just think they are. Okay, back to the pennies. I want to know how big of a sample size do I need if I want to be within 0.005 grams for my margin of error and a 99% confidence. We're assuming that the standard deviation is 0.02. So that's another thing with when we're finding the sample size is we don't have a sample yet, so we don't have a sample mean. So we have to assume our population standard deviation. So we're just assuming. Or it could be on a previous sample or something. They're just going to say assume, or they're going to give you a sigma. So let's go back to our Z table because we're using Z-scores. 99%, I'll write this down. The 99% Z sub alpha, alpha divided by 2, is 2.575. So we found that right here with our critical values right there. Go back. So whoa, I hate when I do that. My margin of error that it gives me is 0.005. And my standard deviation is 0.02. This is all we need. Okay. So I'm going to do n equals, it's supposed to be little n. Samples are little n. What the heck am I doing? Okay. 2.575 times, I'm going to use parentheses, 0.02 divided by my margin of error, and then square it. If you are a good steward of your parentheses, you can put this whole thing into your calculator.
That's a T, right? Or yeah, T with the sub alpha
No,
divided by 2.
it's a Z because
Oh, it is a Z.
we cannot use a t-score because we don't know the sample size.
Okay, gotcha.
Yes. If somebody check my math, tell me if I'm wrong. So I typo queen here.
That's what threw me off on the last problem of my open math that I emailed you about, because you said to use inverse T, but I didn't have the degrees of freedom to
Oh,
use
okay.
inverse T.
Oh, gotcha. That's struggle. I'll have to look at that one. You can send me a message again if you need to for me to look at it, unless you figured it out.
I figured it out. I ended up using the Z-score.
Oh, okay. Perfect.
Thank
Okay.
you.
You're welcome. So I got 106.9, which means we round it to 107. Remember that we always round up. So I would need 107 pennies to get a margin of error of 0.005 and a 99% confidence. I believe we have one more.
I think I just missed it when you just said, so even at 106.09, you'd round up to 107?
Yes, because 106.0, 106 is still too small to get exactly what I want. We have to round up, always round up. Now, if I had 106 exactly, which like never happens, we'd just keep it. But this is 106.09. It's still greater than 106. So like before, even if I only had 5 extra kids, I need to get another bus to fit everybody on there for the safety, whatever. So I have to get another bus, 107. We're gonna do one more. I thought we were gonna do one more. We still might do one more. Okay, this is their math. There's one more. All right, let's do another one. We're gonna do the Ford Focus. How large of a sample is required? So we're doing 0.5 miles per gallon, 95% confidence. Does it give me it doesn't give me a standard deviation. I'm wondering if we're using our standard deviation. That would be my guess. Let me see what we had for our standard deviation. Let's go back. What was our standard deviation? That's what I'm going to use. It was 36.8. So my S equals 36.8. There we go. That's what I'm going to use. And then I have, oh, I need my Z-score.
36.8 is our mean, not our standard deviation.
I see, this is why I keep you around. Keep me honest. I was talking about this in calculus this morning. You can ask Miss Emily, who's hiding in there. You guys we've been together long enough now. You'll correct my math. First couple of weeks, nobody would have corrected anything. I appreciate that about y'all. That you are now willing to correct me and not just let me be wrong. Thank you for that. I appreciate that. Because we've all getting along so great but now. We're 8 weeks in. We're old pals. Okay. So I have that. I'm going to go back to my Z table. 95% confidence. We're at 1.96. So my Z sub alpha divided by 2. Sorry for my ugly writing. I know you can't see it yet, but you will. My Z score is 1.96. And our margin of error is 0.5. All right, let's rock and roll. So N equals the Z score times the standard deviation divided by margin of error squared. Put that in our fancy schmancy. I got 130.75. We agree? Okay. So that means our N has to be 131. We'd need 131 different people to tell us what their average mileage is on their miles per gallon on their Ford Focus is in order to get that margin of error and that confidence. Questions? The next two slides are pulling it all together and showing you both things at once. The proportions and the means. Does anyone need another moment here? And move on? I'm going to move on. Okay. So starting here, this is what the problems look like in 9.1 versus 9.2. So 9.1, you will see the word proportion. In 9.2, you will see the word mean. This is kind of what the problems will look like. So 9.1, you're going to see the words proportion. 9.2, you're going to see the word mean. That's how you differentiate between the two problems. One talks about proportions, the other talks about means. All right, I'm going to go to the actual math. I'll give you a second.
I think on mine, I have a printout. Mine says, oh wait, never mind. I'm looking at the wrong one. I'm sorry. I was looking at the next slide.
It's all right. Yeah, the next slide has all the math. Okay, let's go to the next slide. Oh wait, no, it doesn't, does it? This one asks you is words about the sample sizes. So this one
Yeah, I
doesn't
was,
have the math. The math is on that other sheet that I showed you guys on Tuesday, where that sheet is that shows you the different formulas. But I mean, I could put them here. Hold on. So I could put them here. So for the, I would do p hat plus or minus my z sub alpha divided by 2 times square root of p hat times 1 minus p hat divided by n. This is this right here is, whoa, this right here is, oh, there where's my n go? Margin of error. Okay, there's the math. Then with the mean, what we just did, I have x bar. That's not the bar. Apparently I lowered the bar. Plus or minus the t-score times s divided by the square root of n with n minus 1 degrees of freedom. Okay, so there's the math for that. And this is my margin of error. And it's on that printed that paper that I showed you guys. Okay. Now we're going to move on to the sample sizes. So once again, what you're going to see is something like this within 3 percentage points. And you might see something about a supplemental survey or a previous survey. That's ugly. Or something like that. You may or may not see that, but something like this, it'll say like within 3 percentage points. If it's looking for the sample size, it'll mention something about percentage points. So let me see if I have this memorized. N equals the P times 1 minus P from our previous survey. Is it just the Z sub alpha divided by 2 divided by N squared? I think that's it.
Is it the square root of n?
Is it the square root?
I think it is. I don't know. I gotta look at my notes.
I have a hard time remembering it. This is one of the reasons I let y'all use notes on tests is because
Okay, no, it's not.
did I get it right?
Yeah, you got it right.
Okay. Woo, look at that. Look at me go. Okay, and remember that if there's no previous study, use 0.5 for P.
On the cheat sheet, it has where you have an N in the parentheses, the Z divided by the N, it has an E.
Oh, yeah. That is what it is. You're right. Thank you. It's margin of error. I knew something was off. Thank you so much. I see. I didn't remember it as much as I thought I did. I was really close though. Okay, yeah, I forgot about that. So that's the margin of error. Okay, so I do have this one because we just did this. You watch, I get it wrong. So here I have n equals, and it's z sub alpha divided by 2 times s divided by e squared. And notice it's going to say estimate the mean. It's going to have the word mean in there. It's going to talk about estimating the mean. Plus something here is that there's going to be units here. So on the 9.1, it's going to say within like 3 percentage points. But 9.2, it's going to have some sort of units like miles per gallon or I don't know, degrees or something like that. It's going to have some units because our it's not just percent, it's actually some actual measurement. So that's the breakdown of that. We're still got to do the lab, but before we move off the lab, any other questions about the lesson? Okay, we're going to pop over to the lab now. So for the lab, you can just use your continuous data from previously, from lab 1 and lab 2. You can just use that same continuous data. Now, you are more than welcome to, if you want to use your the data that some of the data you collected for your final project, if you want to just kind of take it for a spin, absolutely go for it. You don't have to. I'm just saying, if you just wanted to throw that in there, it doesn't matter. So you only need 20 data values. It says 50 and on the instructions here, but you only need 20 data values. Because I don't, that's kind of the reward for paying attention to instructions. Once again, we're going to use the descriptive statistics. So remember that box that we enabled, we're going to be using that. So I'm going to go to my data tab and click on the data analysis tool. So it should still be enabled. If it isn't, you're going to have to go back to week 2 or 3. I think it's week 3 and check that out. Should still be enabled on your computer. The data analysis tool, and I'm going to go down again, go to where were we before? Descriptive statistics. Click OK. Now there's going to be a little bit, this is going to be slightly different than what we did before. So first, I'm still going to do input range, and I'm going to highlight all of my data. Still the input range. And my output range is still going to be where I want it. I'm going to put it in this box right here. It's my output range. I didn't really mean to do 4, but that's okay. All right, so what I want you to click on, we want summary statistics, but we're going to do a confidence level right here, because that's what we're doing is we're creating a confidence interval. You don't have to use 95. 95 is just default. If you wanted to do a 99% confidence interval, you can. Or if you wanted to do some funky value, you can. I don't care if you did 83.4. That's weird, but you absolutely could do that if you wanted to. So put in your confidence interval, click on summary statistics and confidence level for means. Okay, I'm going to click OK, and it's going to pop in there. I'm going to make it bigger. Okay, so my margin of error is right here. This where it says confidence level. See here, 99%. This number is my margin of error. So once again, I'm going to go in here, equals, and then margin of error, and hit enter. So the confidence level is the margin of error. The mean is still the mean. My lower bound, so we're going to do math in here. My lower bound is going to be the mean minus the margin of error. So I'm going to do equals, click on mean, then minus margin of error and hit enter. And it's going to give me that lower bound. Upper bound is the mean plus the margin of error. Click on equals, the mean plus the margin of error. Just type it right in there and hit enter. So this gives us my upper and my lower bounds. So what we're kind of doing down here in the interpreting results is it's kind of scaffolding. So it's giving you bits by bits. So right here, what am I estimating? So since my data, it has to do with earthquake magnitudes, I am estimating the actual average earthquake magnitude, actually the actual maximum earthquake magnitude in the world. So whatever yours is, you might be estimating the actual average temperature. So you're estimating a population mean. That's what you're estimating, however you want to word that. But make sure it's in the context. Make sure you mention what your variable is. You're estimating the temperature. You're estimating an earthquake magnitude. You're estimating somebody's height. Whatever you're estimating, make sure that you're mentioning what your variable is. How confident are you that your population mean is in your interval? I chose a 99% confident level, so I'm 99% confident that the population mean is in my interval. That's what I'm typing. Down here on number 3. This is where you write your conclusion. I am 99% confident that the actual average maximum earthquake magnitude in the world is between 6.8 and 7.29. I have a really bad data set, but you could say something like, I am 99% confident that the actual height of an NBA player, actual average height of an NBA player is between 6.9 feet and 7.2 feet tall. I don't know, I'm making stuff up, but you kind of get the picture. So this is where you actually write your conclusion. So it's kind of scaffolded. What are you estimating? How confident are you? And now write your conclusion. That's it. You can do this whole thing in 6.8 minutes or less. Questions about the lab? The intervals are the lower bound and the upper bound are telling you the maximum and the minimum of the values between which you're going to find your actual average. So it's like it's a range of values that the average could land in. Did that answer the question? Yes, okay. Anyone else?
Is the video you uploaded about the lab, is it like the same instructions or did anything change from that video? Because I was gonna like use that video as I did my lab to make sure it was lining up.
It's exactly the same, and it's probably even using this data.
Okay, thank you.
You're welcome. That was a good question. Nobody's ever asked me that before. But I know that the pre-recorded videos, I've improved. I'm a better teacher now than I was back then. So processes are still the same, but it's better now. But yeah, the video is right on. It's a good video. Right. Any more questions while we're still recording? Okay, I'm going to turn the recording off. Maybe. Do this every time. There we go.